Hi, good morning to all of you. Welcome and thank you for joining the webinar. My name is Bhupinder Singh. I'm the General Manager for SISA Information Security Inc. At Sunnyvale office in California. So today's topic is decoding key management for PCI DSS, and we are going to start now. Before we start, there's a couple of items I just want to go over. So the housekeeping stuff, we welcome questions all the time, and please feel free to type those questions, and we will note down those questions at the end of the webinar. We will try to answer all the questions, and if we are not able to answer at the time, we'll try to send you through the email. So please feel free to type your questions, and they're all welcome. So about SISA, SISA is a leader in risk assessment and information security. SISA has been, SISA was founded nearly 10 years ago, and we have been in business all over the world. We have clients more than 300 organizations, and those are the one we are handling as of today, and they are all from different domains. You know, we have clients from the IT, airline, telecom, you name it. We have every industry we have worked, and we have provided consulting services. Our delivery locations, you know, we have offices all in California, Sunnyvale. We have office in Asia and Middle East. You know, we can take care of any of your requests from any place. You know, the SISA works on a framework in which we define three major services, three major components we look at. So SISA is very focused on providing the services. SISA can handle any of the compliance, risk management, any of the technical services. And then we have a product which we use when we are providing those services, and the product is a security assistant. The main focus of the security assistant is to save time for the IT managers and doing the risk assessment. It has a couple of components: risk management, compliance management, data discovery, and document management. And in the same model, in the synergistic model, you know, we also do the training. So if you look at these three different circles, we look at, you know, depending upon the company, what the needs are. So sometimes we start with the training, sometimes we start with the services, and then we go with the products. So we identify what the company needs, and we go from there. So at this time, I'm going to take a moment to introduce you to today's speaker, and his name is Ranju Vargas Jolly. Ranju has been with the company from the beginning, you can say. He has been with the company for the last 8 to 9 years, and he has all the qualifications to do this today's webinar. He has audited a lot more companies. I'll say more than 100 companies, and he has enough experience to answer any of your questions. He's a lead trainer with the SISA, and he has done many workshops worldwide. And so let me take this moment to introduce to Ranju. Ranju, please take ahead from here.
Govinda, and good morning to all of you. So let me start with the introduction about cryptography. Cryptography is basically a Greek word for any hidden and writing as a means of transforming the data in a way that renders the data unreadable by anyone except the intended recipient. What was originally used almost exclusively by governments for espionage has become a powerful tool for personal privacy today. Every modern computer system uses modern cryptographic methods to secure passwords, stores, and provides a trusted backbone for e-commerce. But more importantly, it's been basically used for across the various entities and companies for encrypting sensitive data like the card number and social security number and other information. Cryptography fits into the CIA triad, as it can be used to ensure confidentiality and integrity of a message. Some forms also provide for sent authenticity and proof of delivery, but cryptography doesn't address availability as some other forms of security do. Although forgetting a password for a user account can certainly lead to denial of service account. However, cryptography is used in many areas for accessing the control systems. Let me start with the history of the cryptography. Cryptography dates back to the 2000 BC, and in the ancient Egypt, it got initiated. So, if you know, the earlier cryptography were the Skytail. Skytail is basically a Spartan method involved wrapping a belt around the rod of a given diameter and length for hiding the message. The @bash, it's an Hebrew cipher which mirrors the normal alphabet. And if you see the Da Vinci Code used the @bash cryptography for obfuscation the data. Then we have the SISA cryptography, which basically involves shifting all the letters by a given number of letters in the alphabet. Then we have the Vigneer, which uses a key and multiple alphabets to hide a repeated character in an encrypted message. With the evolvement of the industrial age, cryptography was moved from a manual exercise to one done by the machines. The invention of cipher disk and routers for this use allowed for the creation of much more complex algorithms. And some of the examples are the German Enigma and the encryption algorithms, which was used during the World War. And now we have the modern computing age gave the cryptography a vast resource for improving the complexity of crypto systems as well as for attacking them. And with the new algorithms like the triple DAS, the RSA, Irgendale, the cryptography has evolved drastically. Okay, some of the terminologies in cryptography. One is the plain text. It is basically a message in its natural format, which can be read by any attacker. The ciphertext is basically an altered message which becomes unreadable by anyone except the intended recipient or the recipient who has the keys for decrypting the message. The key is basically a sequence that controls the operation and behavior of the cryptographic algorithm. Basically, it's the main key which basically can be used for decrypting the data. The key space is basically the total number of possible values of keys which is possible in a crypto algorithm. And the initialization vector or the IV is basically a random values used with the ciphers to ensure that no patterns are created during encryption. So for example, if we have say the numeric 1 and we use say numeric 1, 2 and we use a crypto algorithm to encrypt the numerics 1 and 2, we get one ciphertext. But if we change the 1, 2 into say 1, 1, the ciphertext drastically changes. It happens due to the IV or the initialization vector, which always creates a random value for every encryption. Then we have the crypto systems, which is basically a combination of the encryption algorithm, key, and key management functions, which is used to perform the cryptographic operations. Now, just the various types of crypto systems or cryptographic methods which are available. So basically, we have the symmetric encryption algorithm, which basically provides a fast encryption method, but it just uses only one key. The key distribution becomes a big problem. So, for example, we have the encryption algorithms like the DAS, triple DAS, AES, Blowfish. All these algorithms use the one key for encrypting the data, and for the recipient, we need to have an out-of-band process for the key exchange. While for the asymmetric encryption is basically a large mathematical operations which unfortunately makes the asymmetric encryption much slower than the symmetric algorithms. But in case of an asymmetric encryption, we don't need any out-of-band key distribution because the public keys are always, as you know, it's public as it is. And the asymmetric encryption can be used for scaling better because we only require one single key pair per the entity, so that the scaling up provides much better option while if you're using the asymmetric encryption algorithm. Examples of asymmetric encryption are the RSA, the ECC, or the Diffie-Hellman encryption algorithms. The last or the least is the hybrid model. So in the hybrid case, hybrid crypto system is basically the best of both the worlds. In this case, an asymmetric encryption scheme is used to transmit a generated symmetric key to the other party, and the symmetric key is used for encrypting the data. So we have, using the symmetric key, we have the faster encryption in place, and using the asymmetric encryption for the key distribution, we can easily scale up the entire environment. So this combines the scalability and key management features of the asymmetric algorithms with the speed of asymmetric ones. The secure socket layer or the SSL protocol actually negotiates with asymmetric and symmetric algorithms to use in a hybrid system to protect the TCP connections. So some of the examples of the symmetric algorithms are the DES. DES, or the data encryption standard, is basically a 64-bit key which is effectively comes into around 56 bits in strength. As it's just only 56 bits in strength, it can be easily broken. And the various modes that was available in DES is one is ECB, or known as the electronic code book. Then we have the cipher blockchaining, which is known as the CBC, and we have the cipher feedback, output feedback, and counter mode. So these are the various algorithm modes which can be used while encrypting a particular symmetric encryption. Out of these, if you're developing an application, the cipher blockchaining is the recommended encryption algorithm to be, or the encryption modes to be used for encrypting the data, while the ECB is not recommended either by PCI or SISA. Then we have the triple DES, which improves on the DES encryption algorithm by using a 112-bit effective key length. It uses either 2 or 3 different smaller keys in one of the several modes which is explained above. Now, after triple DES, we have the AES, which basically uses a Regendale algorithm for encrypting the data. The NIST actually replaced the DES algorithm in 1997 with the AES algorithm. The AES algorithm basically supports the various key block sizes like the 128-bit, 192, and 256 bits as well. Then we have IDEA, which is International Data Encryption Algorithm, which operates on 64-bit blocks with around 8 rounds with 128-bit keys, and it is considered stronger than DES, and the IDEA encryption algorithm is basically used in PGP. We have the Blowfish, which is even stronger, which uses 64-bit block cipher with up to 448-bit key and around 16 rounds. It was designed by Bruce Schinier for the encryption algorithm. Then we have the RC4, RC5, and the RC6, which was developed by Ron Rivest, and the RC6 has basically been submitted as a candidate for the AES candidate. Then the various other algorithms like the CAST, SAFER, and the Twofish algorithm. So out of the various symmetric encryption algorithms that are available in the market, we can only use triple DES and AES because that's what's recommended by PCI SSE for both PCI DSS and for developing your PIDSS application. In case we are using triple DES, we need to at least use triple is 192 bit and above, while if you're using AES, we need to use at least AES 128 bit and above needs to be used. But we usually recommend that we need to use AES 256 bit encryption algorithm, which basically provides the best encryption across. Now, coming to the asymmetric encryptions, we have the Diffie-Hellman, which was the first widely known public key cryptographic algorithm. It basically computes based on the discrete logarithms over a finite field. Then we have the RSA, which basically stands for the inventors like Rivest, Shamir, and Edelman. It basically relies on difficulty of finding a prime factorization of large numbers to arrive at the encryption algorithm. We have the LGML, which basically can be used for message confidentiality and digital signature service, and we have the elliptic curve cryptography, which basically relies on computing discrete logarithms over an elliptic curve group. Due to the difficulty of problem, the key size can be much smaller than an RSA, but it still retains the strength of an RSA encryption algorithm. So the currently PCI recommends to use an RSA 1024-bit encryption algorithm for both PCI DSS and PADSS. While we're using the RSA, 1024-bit is good. We usually recommend to go for an RSA 204-bit encryption for encrypting the data. Now the more important question, keys. So this is just a tribal to you. We have something called as encoding, which is basically obfuscating the data, whereby anyone who knows the encoding algorithm can decode the particular data. So for example of encoding are base 64 encoding or binary encoding and etc. While encryption is an obfuscation of data, whereby everyone knows the algorithm to encrypt and decrypt the data, but only those who know the key can decrypt the actual data. So basically, if you are going to use only an encoding feature, then if the encoding algorithm gets compromised, then we are required to change the entire application program in order to change the encoding standard which is used within the application. But in case if you are using encryption and the keys used for encrypting the data gets compromised, then all we need to do is just to change the keys in order to reprotect the data, and we don't need to change the entire application at all. Therefore, we need mechanisms for changing the keys and decrypting the data. Otherwise, because in case if the keys gets compromised, then the entire encryption algorithm gets compromised. So we'll be using a new terminology called decrypting, which basically is the act of decrypting the data with an older key and for re-encrypting the data with the new set of keys. So just a new terminology that we use called recrypting. So as I mentioned, okay, we are using a definite specific say triple-DES or AES encryption algorithm. And what's the use of having a proper key management? So if you don't have a proper key management, then it's basically like locking the door and leaving the keys within the keyhole itself. So coming back to the key management comprises of the following. Basically, the creation of keys. We need to ensure that the keys we generate are a strong and random value. We cannot use a weak keys for encrypting the data because it can be easily brute forced to break the encryption algorithm. While storage of keys also plays a very critical role in the key management, we need to ensure that when we store the keys are stored separately and it's stored in a secure manner so that the attacker or a malicious user doesn't get access to the particular set of keys. The key lifetime or the crypto period, because as the value of the keys deteriorate over a period of time, it is important to change the keys at end of each crypto period. The various crypto period for the various standards like triple dash AES is actually defined in the NIST standard, and the PCI or PCI recommends to follow the NIST standard for the crypto period. Then we have the access of the keys for encryption and decryption. So just encrypting and encrypting data is not enough. We need to ensure that the application provides a feature for decrypting data to whichever third-party application, so to the user which requires the data. So the access of the keys for the encryption and decryption plays a critical role in the entire key management process. Then we have the execution of the key lifecycle and the auditing of the key lifecycle and managing a compromised set of keys constitute the entire key management process. Sure. So let's talk about the creation of keys. Basically, when we're going to create a key, we need to ensure that we create a particular random set of keys. There are a lot of various libraries that's available for generating a particular random function for this particular random key. So if you generate a random key, that will help us to avoid having to manage multiple parties with an independent key parts. So it is always recommended to have a system generated keys instead of a user inputted keys, because it will be easy to manage, and we also reduce the risk of the keys being compromised by the humans. So in case of the storage of keys, we need basically at least 2 keys for the PCI DSS. One is called the DEC or data encryption key, which is basically used for encrypting the card number or any other data which we need to secure. Then we have something called as the MAC or the master encryption key. So the MAC is used for encrypting the DEC during storage. While storing both the keys, that is DEC and MAC, we need to ensure that the DEC and MAC are stored in a separate physical systems, so that if once key gets compromised, the other key doesn't get compromised. You might want to think of some kind of encryption or obfuscation of your MAC, but currently it is not a requirement from PCI to encrypt the MAC. But in order to ensure that we have a better security practice, we recommend encrypting the MAC or MEK using something called as KEK or key encrypting key, that is KEK. So that during storage, all the set of keys are hard-coded. So while generating the DEC or DEK, we ensure that it's generated on a randomly. While when we're generating the MEK, we ensure that the MEK can be either generated randomly or can be inputted by one or two or three different key custodians. While KEK or the key encrypting key is basically generated during the development process and is hard-coded into the application, so that it's within the binaries of the application. So what we usually recommend is basically to create a particular DLL file which has the KEK hard-coded. So this DLL file will be then called upon for encrypting the MAC when the MAC gets generated. Then as mentioned, the crypto period. So we need to ensure that the keys gets changed at the end of their usage period and lifetime akin to the data retention period, which is mentioned as per your security policy or as per the NIST standard. So once we have the data being encrypted, we need to ensure that or decide on how these keys will be accessed. So basically, keys will need to be transmitted across the various components because we'll be storing the deck and mech on a physical separate servers. So we need to ensure that we have some service call which calls upon the either deck or mech, or ensures that the data gets encrypted and sent it across. So it can be like an API calls or a kind of web service calls which we can make. So then we have the execution of the key lifecycle. So basically we have the various set of keys, and keys are the following states at a particular minimum level. So we have the current, so the current set of keys, which is basically used to encrypt and decrypt data. Then we have the retired key, which can be only used for decrypting the data. So a retired key may be, for example, let's say we have a set of keys used for encrypting the data as of now. That key will be called as the current key, and we suspect that that this particular current key has been compromised. Then what we'll do is that we generate a new set of keys and retire the compromised key. So the compromised key being retired can be only used for decrypting the existing data. It cannot be used for encrypting new data. So once we ensure that there is proper re-encrypting that's happening, that is re-encryption, then we make that retired keys into an expired key. So expired keys basically can be only used for decrypting data of a compromised key. And in most scenarios, once the keys are moved into an expired state, then it is deleted or purged from the system completely. And we have the deleted keys as basically an historical reference to the keys which we just purged out. So when you're developing the application or implementing the key management within the organization, you need to ensure that we have an automated key state transition, so that the data retention period is longer than the combined current and retired key lifetimes. So in most scenarios, in the most organizations that we have visited, the execution of a key lifecycle is one of the main challenges which the customer faces. Sure. Now, once we have the entire key management process in place, we need to ensure that we have a proper auditing of key life cycles. This is one of the most compelling reasons for storing the keys, that's deleted keys in the database. So we don't need to store the deleted keys, but we just need to give a reference of that particular deleted key. So like the key value or the hash value, we can just mention in the database to ensure that when a new key gets generated at a later stage, we don't generate a same key which has been already been deleted or purged from our system. And in case for managing a particular key compromise, then we need to have the evidence that so key compromise basically is that it's okay, we have some evidence that some untrusted entity have gained access to the key or a set of keys. Then we want to have that particular our application to have an interface to initiate the transition of the suspect keys to the compromised state, and then initiate a decryption of the data using the new set of keys. So basically, this is one of the main critical parties. Like for example, if we there's a human intervention in inputting the keys, and we know, okay, we suspect a particular compromise of the keys, then the application should have more of an automated feature, or not an automated feature, but an option for making sure that the current set of keys which is compromised is moved into a compromised state, and we have a new set of keys being generated for recrypting the entire data, or so that we ensure that our entire data is reprotected. So that particular feature which the application should have. So So moving out from the key management, we're talking about the various aspects of an entire systems. So basically, in a typical software architecture, we may have various three layers. The layer one will be the producers and consumers, like the users, external systems, and internal processes. Then the layer 2 will be the systems, basically the user interfaces and etc. And layer 3 will be the storage, where we'll be storing the encrypted data and also the encryption keys. So while we are developing our key management application, or we're inbuilding the key management within the application, we need to have something called as the encryption service. So the encryption service is basically an interface which will interact with the stored keys in order to ensure that the data gets encrypted and decrypted. And the application layer doesn't get the keys, or there's no other third-party application which can handle the keys. So what happens is that, okay, if the application wants to decrypt some data, then it either calls this particular encryption services for getting the the keys, that is the DEK, and is stored in the memory, and it's used for encrypting or decrypting the data. Or otherwise, there's even better feature where we can send the data to the encryption service or the key management server, where data gets encrypted and it's sent back to the application for storing it in an encrypted form. So the encryption service. So going forward, when we talk about the key management within the application, our focus is basically on developing this particular encryption service or the key management utility, which can basically manage the entire set of keys for a proper PCI DSS or a PADSS implementation. So, yeah. So just to give a recap, we discussed that we need to have two sets of keys. One is DEK, that is data encryption key. The function of DEK or DET is basically used for encrypting the card number, or for encrypting any sensitive data, or maybe the social security number, or any sensitive data which we need to encrypt. The DEK is generated based on a random function, and is generated at time of installing the application or configuring the key management option. The DEK once generated is encrypted using the MEK or master encryption key, and it is stored as an encrypted string in the database tables. While the master encryption key or MEK, the primary function of MEK is basically to ensure that we encrypt the DEK. So while generating the MEK, we can randomly generate the MEK, or we can have 2 or 3 more key custodians entering the key components for generating the MEK. Please note that if we are having 2 or 3 more key custodians for entering the key components for MEK, then we need to ensure that the key components are XORed in order to get the MEK. Just adding the key components together doesn't ensure that we have proper set of MEK. We need to make sure that the key components are XORed to generate the actual MEK value. The MEK can be stored in the either the DLL file or the config file in the key management server. As we mentioned earlier, it is not an requirement from PCI to encrypt the MEK during storage, but we usually recommend for encrypting the MEK during storage using something called as KEK, or the key encryption keys. And both the keys, that the MEK and DEK, has to be changed at the end of the various crypto periods based on the algorithm which is used for encrypting them. And the algorithms vary depending on the NIST standard. Just a brief outlook on the key management module. So here, first function for any of the key management module is basically to generate the MEK. So we can either generate the MEK using just a random function that's available with that can be configured in the application, or we can have 2 or 3 key custodians enter the MEK to enter their key components together, which can be then XORed together to generate the MEK. Once the MEK is generated, then we generate the DEK based on a random function, and the randomly generated DEK is then encrypted using the MEK function. And MEK gets encrypted using the KEK, which is a hard-coded key, and gets stored in the key management server. So basically, we have the key management server here where the key management module will be running. So once we generate the MEK and DEK, the DEK or the tag gets encrypted by the MEK and is then shared with the database server where it is stored as an encrypted string. While the key management server will, while the MEK will be stored within the key management server, encrypted using the KEK, which is basically a randomly generated keys which is hard-coded within the application. So just to give you a brief overview on the encryption decryption process. So once we receives the card number, the application server then just queries to the key management server or the KMS for getting the DEK data encryption key. The key management server then gets the encrypted the encrypted string of DEK from the database server and decrypts the DEK based on the MEK which is stored within the key management server. And the clear test DEK is then passed to the application server for encrypting or decrypting the data. And the application server basically encrypts the data and can be sent to the database server for storing to the database. So here one of the important points to note is that on successful completion of the entire key management process, the application should nullify all the variables which were processing the keys, whether it be the MEK, KEK or the DEK. So nullifying is just not calling the null function, but actually replacing the variables with zeros, so that the entire data gets replaced with zeros even within the server memory or the RAM memory. Just to give you a more detailed overview of the entire encryption process. So the application server basically gets the request, then the application server then sends the DEK request over SSL to the key management server. The key management server then requests the database cluster or a different database schema for the encrypted MEK. The MEK which basically is encrypted using the KEK. And within the key management server, the MEK is then decrypted using the KEK, which is hard-coded into an DLL file. So once we get the MEK, then the key management server sends the request to database schema 2 for retrieving the encrypted DEK string. And once we receive the DEK from the database, the application actually decrypts the DEK using the MEK, and the DEK is then sent back to the application server for encrypting or decrypting the data. So this is basically one recommended solution. Another better solution is basically for sending the data, that is the card number, directly to the key management server, and key management server does the encryption and decryption. So that is the most ideal solution, but unfortunately, as there are going to be a lot of transactions which may hit on an per minute basis, sending the data to the key management server for encrypting or decrypting the data sounds will have a performance issue. So that's the reason why the DEK is shared with the application server and it is retained in the application server memory. So another under function that we recommend within the application server is that if the DEK is stored in the memory, gets encrypted is in the memory also, so that let's say the application server receives the clear test DEK for encrypting the card number. So once a function exit, then the clear test DEK is encrypted using another set of section keys, which is basically retained within the system memory itself. So that at any point of time, only in time of encryption or decryption, the DEK will be in clear test, while all other time the DEK will be stored as an encrypted string within the application server memory. That way ensures that the DEK is also protected in the application side. Sure. Now, what we covered earlier is basically of having a key management process which we can inbuild within the application. While there are a lot of key management process which is provided by the various database schemas like the Oracle. So, for example, the Oracle provides something called as the Oracle DBMS Obfuscation Toolkit, or DOTK. DOTK is basically it's still available for Oracle 10G and 11G, but it's expected to be labeled as an obsolete by Oracle in the future, because it's promoting the DBMS crypto, which provides a better key management process. In case of a DOTK, we require a manual padding to around 8 bytes boundaries, which is to create DOTK, and we need to we need to have a padding with clear test with zeros, and rather than a random information which weaken the encryption result. So DOTK is basically currently none of the entities use DOTK, and most of them have migrated to Oracle DBMS crypto package, which will be available from Oracle 10G release 1 onwards. The DBMS crypto package basically supports stronger cryptographic algorithms than the DOTK, such as the AES 128, 192, 256-bit, etc. It is also easy to implement since it doesn't require any manual padding of the clear test. The DBMS crypto provides both zero padding and as well as PKCS5, that is Public Key Cryptographic Standard 5 padding. The PKCS5 padding should be used over the zero padding, as the zero padding reduces the entropy and may leave the cipher test vulnerable to cryptanalysis attack.